September. Tonight, without delay, I am so proud to introduce Dr. Holly Michael, who teaches at the University of Delaware in the Department of Earth Sciences and the Department of Civil and Environmental Engineering and the Department of Geography and Spatial Sciences and the School of Marine Science and Policy. She is also the director of the Delaware Environmental Institute and the Unidel Fraser Russell Career Development Chair for the Environment. She received her PhD in hydrology, I got the H that time, from MIT. Her topic tonight is the salt tide, our land, our food, our future. Please welcome Holly Michael.
Thanks so much for that really nice introduction. How's the volume? Too loud? Okay. That better? Okay. All right. I'll try to stay here. All right. Well, thanks everyone for coming tonight. And like Sue said, please feel free to interrupt, especially if something's not clear. But then we should also have time for questions at the end, I think. Okay. So today I'm going to give a lot of background, but I'm also going to show some of our research. And I want to acknowledge that the research that we do is really team science. And so this is the work of many collaborators, many students, and postdoctoral researchers and technicians that have worked on what I'll show you over the years. Okay, so I just want to start with just a cartoon of how I think about coastal water systems. So this is a diagram of coastal groundwater. And so this is, if you can see, this is sort of a cross section where the light blue here is meant to be fresh groundwater. And the darker blue, the gray is meant to be saline groundwater. And so we have the ocean here, and under the ocean, it doesn't just stop at the bottom of the ocean or the bay, right? There's an aquifer under there that has water in it. And so under the ocean, there's saline groundwater, and under the land, there's typically fresh groundwater. And groundwater, a lot of people kind of think of groundwater as being underground rivers. But the vast majority of our groundwater is just in the pore space in sediments, in rocks. And so that's what this is meant to show, is that groundwater is within these sediments. And it moves. It moves depending on the hydrology of the system. And so coastal groundwater is especially vulnerable because it is sort of, I think of it as being squeezed between what we're doing on land and all the contaminants that we generate from industry and agriculture and our septic tanks and things like that. It's sandwiched between those sources of contamination and this infinite source of contamination at the coastline, which is the salt. And so the saline water can move into the freshwater in lots of different ways. And I'll talk more about this, but it can happen due to pumping the water on land. And it can also flood over the land and sink into the fresh groundwater, et cetera. Okay. So the topic today is saltwater intrusion, and I guess I should have said saltwater intrusion is this process of the saltwater moving inland into the freshwater, so freshwater being salinized. And it's been documented on all coasts of the US. This is a widespread phenomenon in coastal areas. And it's also a major problem globally. So I'm just highlighting a few studies here. There are many thousands of studies all over the world where saltwater intrusion is a problem. And it's especially a problem because so many people live on the coast, right? About 600 million people live within just 10 meters elevation of sea level, and 2.5 billion people live within 100 kilometers of the coastline. And you only need a tiny bit of seawater to ruin a freshwater resource. So about 1% you would be able to taste. You probably wouldn't want to drink 1% seawater. And it can also then harm crops and other ecosystems. So, as I said, intrusion of groundwater is the inland movement of it, and I think of it as sort of a seesaw. It's a seesaw between the land and the sea. And so when we're talking about groundwater, this is again a cross section, right? So here's the land surface, fresh groundwater under land, and saline groundwater under the sea. There's an interface between them that is basically the position is determined by the difference in elevation between mean sea level and the groundwater level on land. And it goes underneath the land like this because the saline groundwater is more dense than the fresh groundwater. So the fresh groundwater kind of floats on top of it. That's why it's shaped like that. And then in surface water, it's the same idea where you have fresh water flowing down, and then you have sea level and tides and everything that's pushing back from the seaside, right? And so that salt front, the position of that salt water is determined by that kind of seesaw. Okay, so what causes that seesaw to tilt? Um, One, of course, is sea level rise. So if sea level rises, then Snoopy starts to win. The pressure under the sea is higher, and so that salt water moves inland. And in the red here, I'm showing previously freshwater that becomes salinized. Another problem with sea level rise in coastal areas is that the whole hydrologic system wants to rise too. So the groundwater itself wants to rise in response. And in a lot of systems, like in coastal Delaware, the groundwater is really close to land surface. And so if that rises, it intersects land surface, and then you get groundwater flooding. Um, with climate change and also droughts and things like that, you can have reduced rainfall that causes this water table to drop and this saltwater to move inland. If we pump groundwater, that causes saltwater again to move inland, sometimes in this cone shape. We call that upconing. Storm surges, storms wash over the land surface, sink in because that saltwater is dense, and salinize. And then in streams, it's the same idea with this balance. And yeah. And so the fresh water is coming down. And again, there's a wedge in this tidal river. Okay, so what's the role of climate change in all this? Well, some of it is clear, right? Sea level rise, changes in the recharge to groundwater, meaning changes in precipitation or evaporation, changes in the amount of surface water that's coming down. So that could also be caused by sort of changes in snowmelt and things like that. Coastline migration. So when sea level rises, the coastline itself can move. And that means that ocean surges are going to go further inland, and the surges themselves are predicted to be more frequent and intense. And droughts are too. And so what's happening on land is also important. So this is a study that came out a couple of years ago or last year. The first author was one of my PhD students. I'm not an author on this, but I was very proud that that she first authored this paper. But it looked at she predicted saltwater intrusion globally in 2100, looking at changes in sea level and changes in precipitation, rainfall. And so you can see, so this is no change in yellow. Blue is saltwater retreat, so it got fresher, and all the reds are areas that became saltier. And so very few areas you can see are blue, and the freshening is mostly caused by increases in precipitation, whereas most coastlines become saltier, and some a lot saltier. And what does that mean? So drinking water, of course, is a problem. So, just here are a couple of headlines. There are many, many headlines that we could find of areas where drinking water is being affected by increases in salinity. Here's one on Long Island, another one talking about East Coast drinking water in general. Part of that is due to groundwater salinization, and part of it is also due to that salt front moving up rivers. So this is a news article for an incident where the salt front moved far enough up the Delaware River that they started to worry about the intakes for Philadelphia. And so if you have some time on your hands and you're interested, this is the Delaware River Basin Commission has a really nice website where it actually tracks the position, the measured position of the interface. So I took a screenshot yesterday, I guess, or I took it yesterday, but they update it weekly. And so this was the June 8th position of the front. This pink area is where the front normally is in June. And so we're right where we need to be. That's good. The last time I gave this talk, it was actually pretty far inland of where it should be. This red star is the drought of record. So there was a really big drought several decades ago that pushed it really very close to Philadelphia. The blue square is the intake. Yeah. That's an excellent question. I should have put that down, but I want to say like in the 60s maybe, but I can check that. Oh, sorry. He asked when the drought of record was, and I can't quite recall. Yep. But I can get you that information. Um, Checking to see if it's on here. I don't think so. Okay, but this is something that is really well tracked because it could cause huge problems if it gets up to the intakes, and so here are some reasons why. So this article said saltwater intrusion, should your utility be concerned? And the answer is yes, many of your utilities should be concerned, and there are a lot of reasons why. One is that seawater is really corrosive, even at low levels. And so if we have metal pipes, if we have building foundations with iron rebar, things like that, then they can be susceptible to corrosion. Another thing, and part of the reason that they're so worried about saltwater getting into the intakes to Philadelphia is, of course, we don't want to be drinking salty water, but there are other effects too, because one, if the saltwater gets into the pipes, I don't know if you remember the incident in Flint, Michigan from many years ago, but the issue there was that lead pipes started to leach lead into the drinking water supply, and the reason was that they changed the source of their water supply. It was this time it wasn't saltwater intrusion, but the chemistry of that source water was different enough that it caused chemical reactions that then caused problems for years. And so that same kind of thing can happen if you get salt water into the pipes, right? And so there's the corrosion aspect and the release of contaminants, but also it causes problems with the water treatment. So from the river, it goes into the water treatment plant, and the processes that they use for disinfection, for example, there are reactions that can occur that cause byproducts that are actually carcinogens, right? So there can be health effects due to these sort of chain reactions that happen. And there are a number of other of issues that can happen, right, with sea level rise. So I mentioned the corrosion. I'll talk about that again, and issues with pipes. So if the pipes break, you can get water going in or out of them, causing contamination. Roadbed flooding, but also heaving. So as that groundwater comes up, you get higher pressures. It pushes up the roads. It pushes up foundations and can cause lots of problems. And so this has only really recently kind of been a hot topic of study. But one thing that motivated that, and actually one thing that motivated, we have a working group in the institute that I run on saltwater intrusion and infrastructure. And one reason we thought to look at that is the Surfside collapse. If you remember the collapse of that condominium in Florida. And of course, there are multiple reasons that happened, and there was a long investigation, but corrosion of rebar in the footings is potentially one major reason that it failed, and that was due to saltwater intrusion. So, yeah.
Saltwater studies and does on a routine basis.
Yep. So the question was, are we tracking saltwater intrusion, in the research that we do in Delaware? And we are, and I'll show you that shortly. Yep. Thanks. Okay. And I mentioned already the groundwater flooding issue, again, this makes a lot of headlines. You can see some really extreme examples. This is an example from Ireland where there's just, the groundwater table rose and it's just widespread flooding in agricultural fields. If any of you have been to New Orleans, you may or may not know that there's a massive amount of infrastructure to keep the water out of the city. So there's a whole pumping infrastructure where they're just constantly pumping out groundwater and into the lake in order to keep the streets dry. So it's an extremely expensive, massive engineering undertaking to get rid of this water. Okay. And I think two more on the implications, but ghost forests have been in the news a lot. And so ghost forests are coastal forests that are dying off because saltwater is intruding, marshes are moving inland. Marsh migration inland is not a bad thing. We need our marshes and they're really important. So that's actually, in some ways, they're good, but it's just a really clear visual indication of the change that's happening along the coasts. And there are also a lot of problems with agricultural in these coastal zones up against the marshes and up against the coastlines. So I'll talk more about that. Okay. So what do we do about this? We can monitor the water levels, the salinity of the surface water and the groundwater, the contaminant levels and their mobility, or how they're moving through the system. And we can do this in a number of different ways that I'll talk about. We can do research to try and understand the problem, understand the mechanisms, meaning the physical things that are driving it, and also the economics, the social feedbacks, how are people making decisions around these changes, and try and predict future scenarios so that we can plan. And then communication and education, which is partly what we're doing here. And then there are also different kinds of solutions, and I'll talk about that later. Okay, so one of our research projects that we were doing was in Greater Dover, Delaware, and the reason we're interested in Dover is that it's a really nice example of a place that has salt marsh right up against ag. This is irrigated agriculture right up against the city, and the city's using groundwater, the agriculture is using groundwater, and so we're looking at the implications of groundwater use against the marsh. And so we did lots of monitoring. That's what these locations are. We have groundwater wells. We're monitoring the streams and the marshes and irrigation ponds. They have irrigation ponds there. And here's some of the data, just to give you a sense of what we see. So this is one of our farms. We had a number of wells here. We had some shallow wells that were right up against the marsh. And then we had some deeper wells further into the field near the irrigation wells. And we were monitoring water levels and salinity. Okay, and so the red line is the shallow wells and the blue line is the deep wells. And this is the top graph here is the water level. And so what you see, this is over several years, is that during the summer, the deeper wells are showing evidence of irrigation. Those water levels are dropping during the summer quite a lot. Then they recover in the winter, they drop again in the summer and recover. The shallow wells don't really feel that. You can see that they drop a little bit in the summer, but they're much more consistent because they're not feeling that irrigation. But if we look at salinity, it's a very different story. So the shallow wells actually the deep wells stay very fresh. So they're in here. But these shallow wells get salty every summer, right? And so even though these deep wells aren't actually getting salty, the fact that they're pumping is causing salt water to move into the field and into the soils. So basically we see that there's this interplay between using that water for irrigation and the fields at the edges becoming salty. Here's another example. This is a irrigation pond. So these are dug ponds down into the groundwater table, and then there's just a pump that the farmer will pump and spread the water. Here at the top, I'm showing the water level, and in this case, we have a deep and a shallow well. That's again the purple and the blue. There's a berm between the pond and then a marsh channel. So the marsh kind of comes right up, and there's actually a pipe that connects the two. And originally these ponds were designed like that so that they wouldn't overflow, they could drain to the marsh. But now the marsh levels are high enough that this is really changing. And so we monitored during Tropical Storm Melissa, that's right here. And what we see is that, so I'm just zooming in now into Tropical Storm Melissa. This is the marsh water level, and these are the well water levels. And so clearly the marsh has come above the level of the groundwater, which that means that the water wants to flow from the marsh into the groundwater, and it does. So immediately the marsh and the pond, well, the marsh becomes salty quickly, then the pond becomes salty. And then after a couple of weeks, you can see that that shallow groundwater became salty. So that salt water went into the pond, down into the shallow groundwater. And then several months later, it got down to that deep well. So there's this kind of overtopping and then long, slow transition to salinization. And it takes many months to recover back down to freshwater salinity. So, we did more monitoring than this, and we identified some more mechanisms like this, which I don't have time to show you. But basically, through this monitoring, we were able to better understand how the salinization was happening that was affecting these crops. And we were then able to get better water management through stakeholder engagement. So this was really in Delaware the first systematic study of saltwater intrusion into irrigation water sources, and it caused the Department of Agriculture to acknowledge it, to notify constituents. The city of Dover actually changed its pattern of water use. So the city of Dover has wells in multiple aquifers, but most of the irrigation happens in the shallowest aquifer, and so in the summer when irrigation is happening, they no longer pump from the shallow aquifer so that there's less of a competition. And then also our landowners made some really small interventions that made a huge difference. So just putting in, two-way valves on those pipes, right? The connections and things like that really helped. Okay, so I'm going to shift to a much larger scale now, and I want to show you some data that I think is really, really cool. So the U.S. Geological Survey in 2022 did a survey, an aerial electromagnetic survey all along the Delaware Bay coastlines. And so this survey, if you can see, this is a helicopter, and there's this big sort of contraption underneath it. You can see it's like an octagon. And basically that's sending out an electrical signal into the ground and then receiving it as it comes back up. And what they're able to, and so these white lines are each line that was, so the helicopter went back and forth and then all the way across and back and forth, right? That's what those lines are. And this is the kind of data that you get. So these colors are resistivity, so it's electrical resistance. If it's less resistive, it's because the groundwater salinity is higher, right? It's easier for electricity to go through high ionic strength, to go through saltier water than it is to go through fresher water. And so they use that electrical contrast to identify where there's salt water. And so this is kind of a line showing the various slices, right? And you can see that there's salt water along the bay, as you would expect, and then fresher water as you go inland. They collected almost 3,500 kilometers of lines, which is really an amazing data set. And it, for us, opened a whole new window into what's there. And so this is just to show you what it looks like with depth. So these colors are just, there's a 3D model, and we took a cross section at 5 meters depth. That's what these colors are. But if we look across this line and then look vertically, this is what it looks like. And so again, you can see that there's freshwater on the land, right? New Jersey side, Delaware side, and under the bay, it's more salty. This can see down hundreds of meters. And so these are coastal plain aquifers. They're kind of these layery aquifers, and we're looking down all the way through them. And so one of the biggest things, one thing that this is really important for is being able to just know where that interface is. Because if you think about the way we monitor groundwater is we put in a well. And so we're able to measure salinity or water level at just one little place in this huge aquifer system, right? And a lot of these interfaces are out under the marshes, right? So we don't have wells out there. If we didn't have this kind of image, we would never know where to put the well. Because if you put it in the fresh part, well, even if intrusion is happening, you can't see it. And if you put it in the salty part, same thing. So you have to hit that interface with your well if you want to be able to monitor changes in salinity. So now we know where it is and we know where we can put our monitoring well. Yeah. Yeah. So if I get the question right, it's what are we coordinating across states and with the federal government in terms of collecting this data and being able to create models that can allow us to better manage and make sure there's consistency? I would say yes and no. The states are all different, and they collect data differently. They disseminate data differently. But like we're working with New Jersey closely on this study because we want the same kind of data on both sides, and but the U.S. Geological Survey, they're the ones who did this survey, and so we're collaborating with them too. They do a lot of groundwater monitoring, which is just key to basically every groundwater study. And it's very high quality. They're very careful with it, which makes it expensive, but it's so valuable. And as you said, there's cutbacks, right? And so they're starting to take down some of the monitoring that they're doing, which is a shame, because we have these long-term data sets, and getting those long-term data sets when you're looking at decadal change is just huge, right? So there's some, but it can be a challenge, but yes, the goal would be to kind of have unified understanding, and maybe it will change. Yeah, yeah. Good questions. If I'm going too long, just tell me. Okay, so one thing this allowed us to do, and okay, this is just the state of Delaware, but we could do the same thing in other states. So we kind of did this as a proof of concept. Um, we took lots of different data layers. So the permeability of the aquifer, so how easily the water moves through the aquifers, the groundwater levels, how far you are from the shoreline. Pumping rates, and then also the salinity from the survey, and we combine them together into a vulnerability model, in collaboration with DENREC, the state environmental agency for Delaware. And the reason they wanted us to do this is that they are designing a new saltwater intrusion monitoring network, and so we combine that with the existing wells, which are shown here in blue. Only a handful of them are in the coastal zone, which is a challenge, and most of them are not in the interface. So we were able to identify areas where we think saltwater intrusion is going to occur. And now we know where the interface is there. And so they're actually going to be installing wells. Yeah.
Daniel, my sense is that most um, irrigation wells on the coastal plain are all shallow. Right?
Most of them are shallow in the sense that they're in the first aquifer. They may not be very, very shallow, but like 50 feet. Yeah. Yeah. Okay. I'll switch gears again and talk about one more study that we're doing. And this one is a collaboration among 6 different universities, or 7. Virginia Institute of Marine Science, Boston University, George Washington, Rutgers, Newark, University of Maryland, and University of Maryland Eastern Shore. And we're looking at this problem of saltwater intrusion, sea level change causing groundwater change, and then ecological change. And the ecological change, in particular, we're looking at ghost forest formation and agricultural die-off. And those are due to two primary mechanisms, the salinization, but also drowning of the root zone. So as that groundwater level comes up, the roots don't like to be wet all the time, and that causes problems. So just to give you a sense, hopefully this works. Let's see. Here we go. Let's see. Maybe it won't. It should. There we go. So this is one of our field sites. This is the long-term ecological research site in Virginia, and that's the research reserve. Now we're backing out the marshes behind us, and so you can start to see the trees are thinning. They become thinner and thinner as we go toward the coastline, and now we're getting into the healthy marsh. So this particular site has a pretty thick ghost forest. And so we're interested in studying that transition. I'll show you the map. I'll show you the map in a second. It's down on the Atlantic side of the very tip. Yep. And this is just a little excerpt from a documentary that kind of highlights the problem.
This corn stand was a 100% corn.
Loud. Sorry. I wonder if I could do that without the volume or turn the volume down. All right, maybe we'll skip that. But it's actually shocking what they show. There was one event that just salinized this whole field, and it came up. There are ditches. So a lot of these farmland are ditched because the water table is high, so it drains it. But now the ditches, because the coastal water levels are getting higher, they're reversing. And so a lot of times when you have a high tide event, that just goes right up the ditch and into the field, and the whole field was ruined. So what are the drivers of this change? We've talked about this before, but basically I think of this as slow processes and fast processes. So we have the slow sea level rise that causes that flooding and slow saltwater intrusion and a water table response. But then on top of that, we have our storms, we have our high tides, right? So these things superimposed are what are kind of like ratcheting that salt inland. And so if we think of this as a plot of salinity versus time or versus distance, then if this is the salinity here at which the plants become stressed, right? It's okay. Plants become stressed and then they recover, right? So, okay, salinity goes up and down and the plants can be okay. But then you superimpose that slow sea level rise. And at some point there's a tipping point where they just can't recover after these events. So that's what we think is happening. We're working all around the Delmarva. As you know, it's low-lying. It has one of the highest relative sea level rise rates in the world. That's because of the isostatic change from the last glaciation. Lots of storms, lots of ecological change. So here's the map. We have 6 sites, or 2 in Delaware, 2 in Virginia. This is that LTER site, and 2 in Maryland. And for each set, one is marsh to ag and one is marsh to forest. And what we're doing is interdisciplinary work. That's why we have so many universities and researchers involved. We call this eco-hydrology of ghost forests, and also marshes and farms. But basically, we're measuring the hydrology, so water levels and salinity and soil moisture. We have ecological data, so ecologists have sensors in the trees that are monitoring the water going up the trees, so sap flux and biomass and vegetation surveys and things like that. And we have biogeochemists who are looking at, well, what does this do to the carbon stores? What does this do to, are we releasing lots of nutrients from these ag fields that are becoming saline? And we have all this instrumentation along transects from healthy marsh to healthy upland and through that transition zone in order to understand what's happening. And the goal is to be able to predict how the systems will evolve. So if you go online to NOAA or USGS. They're tools where you can say, okay, if sea level rises this much, how much of the land is going to be inundated? Where are marshes predicted to move? That's all based on static conditions, right? So let's just move it inland based on topography. But we know that these systems are really dynamic. And so what we want to understand really is what are these interconnections so that we can understand how it will really evolve. And so for example, if things were like this and nice and static, we would just expect the rate of change to equal the rate of sea level rise, right? Horizontally. But that's not what's happening. So this is a study by one of our collaborators at VIMS where they used satellite data and aerial imagery to map that marsh forest boundary between 1984 and 2020. And what they found was that the average retreat rate was about half that of the measured sea level rise over that time period. And so there's some kind of lag or there's some kind of buffering that's happening that's causing the change actually to be slower than the rate of sea level rise. But we think in the field, it's actually happening faster. So for example, one of our field sites, our Maryland site, these aren't the greatest pictures, but in 2020, the study started in 2020. It was farmed. It was fine. There's a big healthy zone that we had our wells in, and now well by 2024, the marsh vegetation started to move in. These are like shrubs and things like this and starting to get into these the marsh vegetation, and so the farmer doesn't farm any of the field anymore, not just the fringes, but nothing can be farmed. So that change happened way faster than we thought. We thought in a 5-year study, we have kind of space for time, right? But we're not really going to see the change, but we have. So what we're trying to do is collect lots of data, understand these connected processes, and then put them into models, like you mentioned, so that we can try and predict what's going to happen, but then also think about what if we implement different management alternatives or different strategies for dealing with it? So, basically, we know these shifts are happening, but these feedbacks among these different components and what we do on the land is really going to determine how quickly things change and how it affects our economies and our health and things like that.
Everything's getting hotter.
Yeah.
And so it's like tropics are moving north. And so it's not only the salt water, but you've got the rest of the climate in the field.
Yeah, that's right. And so we're measuring that as well. We're measuring temperature, we're measuring changes in rainfall. And so the question was, yeah, I actually deleted those slides, but drought is a huge driver here. Not because of a lack of water, there's plenty of water because of what it does to the salt. But yeah, so the comment was that, it's not just sea level rise and salinization. The whole climate is changing, and basically climates are shifting. We're gonna be Florida soon. Not that soon, but as things shift, the vegetation is obviously going to respond. And so you're right that it's not just one thing that's causing the change or the buffering. And that's why we want to figure out how do these things interact and really predict change in the whole system and not just like, where's the salt front? Yeah, exactly. Yeah. Yeah. Great point. Okay. So I'm almost done. Oh, I guess we're still okay. Okay. So, yeah, we're okay. So I just wanted to talk a little bit about the various potential solutions that there are. And there's management, there's engineering solutions, there's green infrastructure, science-based policies. I'll focus more on the 3 that are in bold. Well, I guess this is an engineering solution. So desalination, you've probably heard of. That's an engineering solution for dealing with saline drinking water, right? So there's a big desal plant in Cape May that was installed in 1998. And there's a whole story there about the groundwater depletion that caused the saltwater intrusion, that and then they had to install this plant. And more recently, they were thinking they might need to install another plant, right? And the thing about these plants is, and there are desalination plants all over the world, but they're really expensive. So it's basically reverse osmosis. You have to take energy to push, to take the salt out of the water through a membrane, typically. And so there's this trade-off of clean water versus energy, and yeah. So while that's a potential solution, it's expensive, and it's also, I mean, it's pretty much not possible to do the amount of irrigation that we currently do with, say, desalinized water, right? That would be doing desalination on a massive scale. Artificial recharge is something that is done. So this is just an example of one potential configuration of artificial recharge. But basically, you can you can inject water into wells, and you can also pump in different ways that would keep the interface strategically where it is and not cause it to get to the pumping well, right? So if this is our aquifer, here's our pumping well. Under normal, without an injection well, we would just lower the groundwater table, cause this intrusion. But if you have, say, treated wastewater or something like that, you can inject that water. It increases the groundwater levels, and it causes this hydraulic barrier. So that's done in places like Florida, for example. That has its own potential problems, but that's one potential solution. But again, that's energy intensive, right? Because it takes energy to inject that water. The Mississippi, this was an article a couple of years ago where there was a big drought actually in Minnesota at the headwaters of the Mississippi that caused a reduction in the flow in the Mississippi and caused that salt front to move really close to the intakes for New Orleans. And so there was a lot of worry about that. And again, so this is this is the freshwater coming down. There's a saltwater interface, a freshwater saltwater interface, and then the saltwater here. And so, here's where these were meeting. I flipped that around so that it's oriented the same way as this diagram. But the idea is that, so the salt wedge goes, it's further inland at the bottom of the river. And that's, again, because of this density gradient, right? And so the idea is that you can put an engineered sill in here to block that bottom part. And then the fresh water just kind of goes over it, and you don't get the intrusion that you would see otherwise. And so that's something that is actually implemented when they have these extreme events. You might hear about green versus gray infrastructure, natural versus hardened shorelines, right? So you could put in seawalls like this, but there are also other strategies like sand dunes and open spaces and oyster beds and allowing wetlands to migrate and things like that are considered nature-based solutions that similarly protect from flooding, but have some ecosystem services, right? They have some value aside from just preventing that flooding. Yeah. So yeah, the comment was, it's not just that there's increasing water levels and salinity, but there's also there are water quality and ecosystem changes that are happening as well, right? And a lot of that is due to excess nutrients that are getting into our coastal waters, right? That cause, if they cause algal blooms, they can be harmful algal blooms, but also the algae then decompose, that consumes oxygen, and that can cause fish kills, and it just really disrupts the ecosystem. And some of that ecosystem, for example, oysters are naturally cleaning, they're cleaners of the water. which is an excellent segue into my next slide, which is this, which Sue is the article that you pointed me toward. So this is a living shoreline it's an experimental living shoreline that was just installed a couple of weeks ago in Lewis, Delaware. This is part of one of the projects that the Delaware Environmental Institute, which is the institute that I direct, this is one of the projects that we manage. I'm not personally directly involved with it, but we all work closely together. And so this is an artificial reef with oysters. The idea is that you get the artificial reef is a physical barrier, right? But then if you colonize oysters on it, you also have this beneficial water quality impact. And, hopefully over time, these things start to naturally grow and it doesn't look like these weird pots, but it looks like a really nice reef shoreline. So that's just one example of the kind of thing that can be done. And so this is a research project. And so they'll be monitoring what before and after flooding and water quality and things like that to see, to test this out. Then one last slide, I think, is another potential nature-based solution is allowing marshes to migrate. So this is a study that we did. It was a modeling study where we allowed artificially in our model allowed marshes to migrate onto agricultural land. And then we looked at what was the benefit to the land behind it, right? So you're economically losing the land that you allow to become marsh, but are you protecting therefore the land behind it? And what is the relative amount of benefit in terms of the crop loss and money spent on the seeds in the areas that aren't that aren't productive and things like that. And what we found is that economically it's kind of you kind of break even in most cases, right? Where the loss of your farm field kind of balances out the benefit. But then if you consider all the benefits of marshes societally, right, to our ecosystems, to water quality, things like that, then allowing the marshes to migrate just way outweighs it. And so we actually had a conversation with part of the Delaware congressional delegation yesterday or the day before about potentially thinking about policies that would allow farmers to get easement funds for allowing these marshes to migrate and what that would look like and things like that. So that's a potential policy solution. So allowing the change might actually slow the change. Okay, and then I'll just close with two thoughts. So saltwater intrusion is a complex issue. It's growing in the Mid-Atlantic and the US and worldwide. And mitigation and prevention requires collaboration among all of us, and I showed you some collaborations among different kinds of scientists, but also the policymakers and communities who care about these things, who can actually, create some will to make positive changes happen. So thanks, and I'll take any other questions. Hmm. Yeah, we're data poor for AI, but yes, we are using a little bit of AI. Well, let me see if I can paraphrase your. Yeah. So the question was, this is a problem everywhere, and there are other countries who are probably ahead of us in terms of how well funded their science is, and how well they're dealing with these problems. And I would agree with you. I mean, in some ways, we're way ahead of many countries in terms of our. The USGS monitoring infrastructure is pretty amazing, but there are some countries that are like heads and tails above us. One example is the Netherlands. And the reason that's the case is that they have to be, right? Or they would not exist. And they've been engineering their land for hundreds and hundreds of years because they're below sea level. And so they're actually a case where the Netherlands has a lot of funding to work all over the world. And I've worked with some of their scientists in Bangladesh for these kinds of issues and collaborated with them in New Orleans. So there are definitely cases where there's technology transfer among countries in terms of what are the best practices, how do we assess this. I have a student from the Netherlands, a PhD student, and when she was working in the Netherlands, she came here and she looked at our monitoring network and she was like, this is terrible. I can't believe this is all you have, because they have wells everywhere and just unbelievable data sets. But I would say that's that's an exception. That's a rare case of really a lot of infrastructure because of necessity. And that's the thing, is it seems like it takes the necessity to make it happen. But I think understanding what's going to happen and kind of getting ahead of it puts us in such a much better position. So, yeah.
Delaware, the Delaware Bay, full climb book, restoration at Allen Beach, seen as an incredible success story. Money for Sandy money is used to create what kind of an inland freshwater area is now moving freshwater water, great for nesting birds, these terns, leisure catching type of birds. Can you speak a little bit about that story, and if you see that story?
So I don't know a lot of details. What you just described is basically kind of the extent of my knowledge. She said that there's a really nice example of a success story at Prime Hook where they converted what was a freshwater impoundment. It was a false impoundment, like designed basically for duck habitat and things like that, right? But as sea level rose and as Hurricane Sandy hit, it became clear that maintaining that impoundment was just not going to happen economically. Am I right? And so they had a huge restoration effort that then restored it to what it naturally will be, which is a saltwater pond. And yeah, so from my understanding, that is a success story, right? The wildlife is coming back, and in many ways that's kind of what's going to be happening over and over. So one study we did kind of looked at which freshwater wetlands are going to become saltwater wetlands, right? And so there's the same kind of ecological shift is going to happen there. So yeah.
From 15 of it, red line and Newcastle all the way down, basically to Lewis, that part of and mosquito ditching, done for duck habitat, 30s and 40s, follow up. That's all freshwater. So, I mean, what happened to Pine Hook? There were monies for it being standing, but yeah, I mean, that you see that happening up down the coast, and it's farmers might not like it, but it's been really well.
Yeah. I'll give a caveat though. Going further north, where she said there are these freshwater impounded wetlands like all the way up into northern Delaware, and once you get up into Wilmington, there's a lot of legacy contamination, and so like for example, the DuPont Reserve right in Wilmington, if any of you have been there, that was built basically, I mean, it's on contaminated land, right? It's like basically impounding contaminated lands. And so another aspect that we've studied a little bit is, as that right now that's not salty, it's still fresh in the river, but as the salt front comes further up, if that becomes salty, a lot of those legacy contaminants can then be released. And so that's like arsenic and chromium and all sorts of heavy metals. And so that could be an additional potential problem. So in some cases, ecologically, it's good, but there are also, human induced issues. Yeah. The question is, are there opportunities for volunteers to help monitoring? And that's a great question. We have not, my group has not had, community efforts for helping, but we would certainly be open to it. I mean, we always could use more people in the field to help. But there are some, citizen science initiatives. I don't know if there are any specifically around saltwater intrusion, but if you're interested, I can, yeah, talk with you more about that. Yeah. Yeah. Thanks. Thank you. Thanks for listening. Thanks for all the good questions.
Thank you so much. Great. Would you like a piece of cake now or something to eat? Cake?
I maybe I'll go check it out, but